Also a student-based education, and it's suitable for creative work, active student participation, which is not always easy, measures whether a person can think in a disciplined way, project team-based learning, and more infrastructure teacher time. So it's not cheap and very expensive. So how did the universities respond to that challenge? Now, Michael Veritas was the head of the naval architecture at University of Michigan, and he wrote in about 8 years ago that engineering for marine environment at an American research university, that the following changes happened. The new curriculum in 1994 had additional courses on manufacturing, life cycle for industrial design courses for the second year. And before the third year, 4 courses were given. All of this material was provided to the students. In 1997 and 2000, they increased the amount of courses for teamwork, communication skills, ethics, and environmental awareness. And then they increased the simulation-based environment to test virtual prototypes. That means computer-aided design is introduced in the third year and the fourth year. I was really stunned by the ability of the students in the University of Michigan. One of my students there, in the fourth year, was able to calculate the flow on the 3D keel of a sailboat, and he did that not a thesis, but only for 20% of the course credit. And we learned that in 2003, MIT came up with OpenCourseWare. So you have lots of material available to you, to the whole world actually. And they are not classical textbooks. They have lots of software that will allow the student to see the waves generated by a moving ship. So the concept of the open source is very, very different. You have also other material. Now, similar things happened in my university in 2004. What happened is that the first year courses, instead of teaching physics, we introduced statics in the first year. And maybe more important is the inclusion of that engineering fundamentals that was really geared to help the student understand what the design is, what timing is, the budgeting is, and so forth. And it was a big success because students gained lots of momentum in designing. Now, this is a first-year student looking at the machine that they were able to design. This involves a steer ball, and the steer ball is sent up by air pressure and does certain work, and finally reaches the bottom. Now, the project also says the oral and written presentations to the professional engineers. So we are not the instructors were not the target, but we asked the professional engineers to judge the presentations. Now, we included a hovercraft design competition for the second year. The students measured the pressure field around under the hovercraft. They were able to measure the thrust by fans, and later on they included a computer board to measure the current and the voltage, so that the winning team had to have the best transportation efficiency. This is also an explanation of the teamwork that they were able to put together, because some of the students in a team, they were specializing in electrical engineering, some of them in structural, some of them mechanical, so they have to work together and put the system properly. We did similar things in UBC. We introduced computer fluid dynamics. in undergraduate program, we did lots of conceptual development, such as the boundary layer flows in it. And we asked ourselves if we can actually teach boundary layers in a more effective with the help of computers, so the CFD, and a little bit of lab. Now, of course, we all ask ourselves, what will the future jobs of engineers? Will they be using analysis the way my generation did, or will they be using finite element method or CFD or commercial code to study exams, loads, and pumps? And what do they really need? I personally don't know. I can only guess what they need, but I believe that the fundamentals should be there so they can renew themselves during the 30 years that they have to work. And we expect that the fourth-year students should be able to do almost professional work with the help of computer design tools. Something like that is expected from a student. We should be able to explain what each items or where they are located. It's not enough to have just a line story. And this design actually received an award from Photoshop. Photoshop is a software that we use for all design. So what's the end? Do we have to have a digital everything? Or how do we respond to readiness gap? And how to effectively use digital tools in education? My result is that a piecewise solution is not a good solution, but an integrated approach probably will be more effective. And my suggestion is to bring modern engineering practices to the classroom, and that means software and hardware, modify education to stress teamwork, design, creativity, synthesis rather than analysis. Leave as much as possible the numerical studies to computers. Don't compete with computers. Bring numerical analysis tools such as B-splines to the undergraduate education. So we need to change. We need fluidity. We should not compete with computers. We should give tools to our students to design machines that they can imagine. And industry is way ahead of us in computer engineering because they need those tools. They use that. And we should increase the numerical digital components of our courses. So we should stop imitating all masters as what kids did or gauguim did. There are lots of case studies developed in the United States that one can obtain very easily. Students do an excellent job in learning when computer-based tools are available. They love computers. The analysis-based undergraduate course component should be definitely reduced. Can be explained with numerical tools. Unfortunately, we need to invest. We need an infrastructure, something like Media Center of Michigan, gain support of Michigan, digital classrooms of University of Toronto. And most difficult, I think, is we have to change our minds first. I want to skip this. I think the benefits will be our courses will be more relevant to the industrial requirements and the applications. Student design ability, self-confidence, teamwork, retention of the knowledge. I think this is a very important thing. Will be measurably harder, is measurably harder, and they can compete with the other university students. Our undergraduate and graduate programs will be equally more successful. It seems we need to review our curriculum. In the next slide, closing remarks. To progress, we need to change. To change, we have to change our mind first. And changing and thinking takes time. We need to integrate computers in our courses, teaching and engineering. And possibly, we can do that under a wise digital curriculum. Thank you very much.
Contribution to our conference.
Thank you very much.
But we have three presentations. One in the economics of shipbuilding,